Jai Shri Krishna Mitro. Last time we can discuss about the optical isomerism, in which we can discuss about the chirality and a chiral carbon or chiral atom, in which we can say that the compound which can be shows the optical isomerism is disymmetry or chirality is present in this compound, and we can say that if disymmetry and chirality are present in this compound, therefore the compound become optically active. And in very simple language we can say that non-superimposable mirror images are also optically active, which is known as pair of enantiomers. Clear? In which we can study that if any compound have a one chiral center, if any compound have a one chiral center, then 100% confirm the compound is optically active. But if any compound have more than one chiral center, therefore we cannot confirm say that that is optically active. We can say with the help of some factors, and these factors which you can study in this lecture. Clear? So suppose if we can have the compound like that, some topics or some points we can revise it. First of all, if you can have a compound like that, C, H, H, OH and Br, if anyone can say that this compound is optically active, the first way is that we can take the compound and make the solution and fill the solution in a polarimeter, and we can measure the rotation. But it is a not convenient method in an examination hall. Therefore, we can say that we can think with the help of structure. If we can think about this carbon atom, there is two valencies are same, means that all four valencies of carbon is different, then we can say that this is a chiral carbon. But here two valencies are same, therefore there is no chiral atom or no chiral carbon in this compound, therefore this compound is optically inactive. Therefore this compound is optically inactive. Suppose if we can have a compound like that, COOH, C, HOH, OH. If you can think about this carbon, these two valencies are same. If you can think about this carbon, therefore also two valencies are same, because C double bond O means that it is double bonded to O, and hybridization is not satisfied. First condition is that the atom is in a sp3 hybridization. Clear? Therefore this compound is optically inactive because of no chiral center. Clear? Any atom which can become a chiral if it is sp3 hybridized, and four valencies of this atom must be satisfied with four different groups or four different groups of atoms. Clear? If you can have a compound like that, CS3, Cl, Br, CS2, CS3, and anyone can say that check it is optically active or not. It is not a chiral carbon, it is a chiral carbon, because one is CS3, second one is Cl, third one is Br, and fourth one is that ethyl group. Therefore this carbon is a chiral center. This is not a chiral center because it can have two hydrogen, it can have three hydrogen. But this compound is optically active because it can have only and only one chiral center. Clear? Now suppose if we can have a compound like that, COOH, H, COH, H, COH and COOH. You know that this is a Fischer prediction. Clear? Now if you can think about these carbons, it is chiral carbons because first valency is H, second valency is COOH, third valency is OH, and fourth valency is that. Then four valencies are different of this carbon. Therefore this carbon becomes optically this carbon becomes a chiral carbon. Same situation here. First valency is H, second is OH, third is COOH, and it is the fourth one. Four different valencies are there. Therefore you can say that this compound have two chiral centers, but we cannot say that it is optically active. This compound is optically inactive. It have two chiral center, but it is optically inactive. Then the question is that why? If compound have a chiral centers, then why it is optically inactive? Then we can think about the disymmetry. Then we can think about the disymmetry. Clear? Disymmetry means no symmetry. What is the meaning of disymmetry? No symmetry. Compound does not have any symmetry, then therefore it is disymmetry. There are four types of symmetry are there. First one is COS, POS, second one AOS and AAOS. Now it is a types of symmetry which can be or which may or may not be present in the compound. First one is center of symmetry. COS means center of symmetry. POS means plane of symmetry. AOS means axis of symmetry. AOS means axis of symmetry. AOS means alternate axis of symmetry, but this type of symmetry is not in our syllabus. Clear? Now we can think about the 4 types of symmetry. What is the meaning of disymmetry? Disymmetry means no symmetry. First symmetry is COS, second one is POS, AOS and AOS, but it is not in our syllabus. Clear? Center of symmetry, plane of symmetry, axis of symmetry and alternate axis of symmetry. If any compound have COS, therefore this compound does not become optically active, means that it is not present in compound. If a compound become optically active, means કે જો કોઈ કમ્પાઉન્ડમાં સેન્ટર ઓફ સિમેટ્રી પ્રેઝન્ટ હોય તો એમાં કાયરલ સેન્ટર પછી કોઈ પણ હોય, કાયરલ કાર્બન કેટલા પણ હોય છતાં પણ એ ઓપ્ટિકલી એક્ટિવ ન બની શકે. મતલબ કે આ પ્રેઝન્ટ હોવી જોઈએ નહીં તો જ કમ્પાઉન્ડ ઓપ્ટિકલી એક્ટિવ બની શકે. યસ, પ્લેન ઓફ સિમેટ્રી પણ ન પ્રેઝન્ટ હોવી જોઈએ. બટ if you can think about axis of symmetry, it may be or may not be. A present હોય કે ન હોય એનાથી ફરક નહીં પડે. We can check first these two symmetries, COS and POS. Center of symmetry present ન હોવી જોઈએ, plane of symmetry પણ ન હોવી જોઈએ. બેમાંથી કોઈ પણ એક પણ સિમેટ્રી જો કમ્પાઉન્ડમાં પ્રેઝન્ટ હોય તો કમ્પાઉન્ડ ઓપ્ટિકલી ઇનએક્ટિવ થાય. પછી એની આગળ કેટલા પણ કાયરલ સેન્ટર કે કાયરલ કાર્બન કેમ ન હોય. ક્લિયર? તો now we can think about that. COS, POS, AOS and AAOX. First of all, we can think about these two symmetries because it is very important. It may not be present in compound. If these symmetries are present in the compound, therefore compound become optically inactive final. Clear? So we can think that, or we can say that in first lecture, compound must be disymmetry. Disymmetry means no symmetry. Clear? Now the question is that if anyone can say that why CH4 methane not show optical isomerism. Why CH4 methane not shows optical isomerism? If we can draw the structure of methane, it is like that. CHHHH. It is octahedral, which you can draw in 3D wedge dash form. Clear? This is optically inactive due to first reason is that it not have a chiral carbon. And second and proper reason is that it can have POS, plane of symmetry, because if we can pass the plane through these molecules, their molecules are cut in 2 equal halves. If any plane which we can pass from the molecule, either side of the molecule, and it cut down the molecule in 2 equal halves, therefore you can say that it compound have a plane of symmetry. It compound have a plane of symmetry. It is not necessary to pass the plane like that. You can also pass like that, like that, like that. But this type of plane cut down the molecules into 2 equal parts. Therefore, you can say that this plane are present for the symmetry. Clear? You can say that plane of symmetry is present in the methane. Therefore, methane does not show the optical isomerism. Now we can think about plane of symmetry and center of symmetry in very deep concept. Now you can study about the different types of examples with respect to plane of symmetry. Suppose if you can consider alphabet A, B, Z, C, D. Now what is a plane of symmetry? We can consider a plane and we can pass from the molecule which can divide the molecule into 2 equal parts or halves. Therefore you can say that this compound have a plane of symmetry. It is the definition. A plane which can be divide the molecule into equal parts is known as plane of symmetry. If we can have an alphabet A and we can pass the plane from here, it can divide the A into 2 equal parts. Therefore, you can say that in A, plane of symmetry is present. In alphabet A, plane of symmetry is present. Suppose if we can think with respect to B, alphabet B, if we can pass the plane like that, here we can pass the plane like that, now here we can pass the plane like that, it can divide the B into 2 equal parts. There is no necessary to pass the plane right from this side or that. You can pass any side. Therefore it is a plane of symmetry. It have also plane of symmetry. Here if you can divide it into two parts with respect to the plane. Therefore, it gives the two equal parts because parts are same. It gives also a plane of symmetry. If you can think about C, it is also gives plane of symmetry. If you can think about D, it is also gives a plane of symmetry. If you can pass the plane from the center of any side, and it can divide the molecule into two equal parts, therefore the molecule have a plane of symmetry. And if a molecule have a plane of symmetry or center of symmetry, therefore molecule does not become optically active. Clear? First example which we can study here is CS2Cl2. CS2Cl2, CHHClCl. If we can pass the plane like that, then it can divide into two equal parts. Therefore, you can say that it can have plane of symmetry and does not show the optical isomerism. And we can think with respect to the chiral carbon. Therefore, also does not show the isomerism, optical isomerism, because this carbon is not a chiral. First, we can think about chiral carbon. If compound have more than one chiral carbon, therefore we can check the symmetry. If a molecule have a one chiral carbon, therefore there is no necessary to check the symmetry generally. But if a molecule have more than one chiral carbon, therefore we can check the symmetry. Clear? If we can have a molecule like that, CCl4, if you can pass the plane from this side, or if you can pass the plane from this side, it can divide into two equal parts. Therefore, you can say that does not show the optical isomerism. This type of compound does not show the optical isomerism. Suppose if we can have a cyclohexane. Therefore, it can have a plane of symmetry with respect to first plane is that. If you can pass the plane from this that side, it can divide into two equal parts. First plane of symmetry. It is second plane of symmetry, because if you can pass the plane like that, it is also gives the two equal parts. It is third plane of symmetry. Clear? It is fourth plane of symmetry. Fourth plane of symmetry. It is fifth plane of symmetry. It is sixth plane of symmetry. And one another is 7, which we cannot draw here. Here we can say that if we can have cyclohexane, we can cut from that, this, and this. And last one symmetry is like that. If we can cut the cyclohexane ring like that, it gives the two equal parts. Therefore, total number of 7 plane of symmetries are present in cyclohexane. Therefore, it does not show the optical isomerism. In many times, question is like that, how many plane of symmetries are there in the compound? Therefore, you can think the possibilities. Clear? There are 7 total plane of symmetries. Seventh one is not shown, because if you can think about this ring, if we can pass the plane like that, it can also divide the molecule into two equal parts. Clear? Now, if you can think about cyclobutane, it can have also plane of symmetry, because first one is that, second one is that, third one, fourth one, but we can think that it can have a plane of symmetry. Therefore, it does not show the optical isomerism. If you can think about 1-methyl cyclobutane, it is also optically not active, because it can have a plane of symmetry. If we can pass the plane from this side, it can divide into two equal parts, because this CS3 is like that, H, H and H. Now we can divide it. Clear? If we can have 1,2-dimethyl cyclohexane, it is also optically inactive, because if you can pass the plane from this side, it can divide the molecule into two equal parts. It can have a plane of symmetry, not shows the optical isomerism. If you can have a 1,4-dimethyl cyclohexane, it is also a plane of symmetry. And therefore, this compound does not show the optical isomerism. If you can have a 1,3-dimethyl cyclohexane, it can have also a plane of symmetry. It is also does not give the optical isomerism. Clear? Now, if we can think about some different examples like that. First is cis-1,2-dimethyl cyclobutane. Cis-1,2-dimethyl cyclobutane. Cis-1,2-dimethyl cyclobutane. Cyclobutane. Cis means if first methyl is upside, then second is also upside. If we can pass the plane from this molecule, it can cut down into two equal parts. Therefore, you can say that it can have plane of symmetry and does not shows the optical isomerism. It can have a plane of symmetry, does not shows the optical isomerism. If you can think about transform, trans 1,2-dimethyl cyclobutane, trans 1,2-dimethyl cyclobutane, if you can pass the plane from the center of any side, it cannot cut down the molecule into two equal parts, because these parts and these parts are different. Therefore, we can say that this compound does not have a plane of symmetry. Now we can check the center of symmetry. If plane of symmetry is not present, then we can check the center of symmetry. Center of symmetry is also not present in this compound. What do you mean by center of symmetry? It means that we can consider a point on a center of a molecule, and from this point we can go through any direction and we can have same parts, same atoms and same groups of atoms. Therefore, you can say that this molecule have a center of symmetry. Means that કોઈ પણ મોલેક્યુલના સેન્ટરમાં મિડલમાં એક પોઈન્ટ કન્સિડર કરવાનું. એ મોલેક્યુલમાં જ, મોલેક્યુલની બહારની સાઈડ નહીં. ધારો કે આ મોલેક્યુલ હોય તો એના સેન્ટરમાં જ, પછી અહીંયા નહીં. ક્લિયર? મતલબ કે મોલેક્યુલની બહાર નહીં, સેન્ટરની અંદર જ તમારે, મોલેક્યુલની અંદર જ તમારે સેન્ટર કન્સિડર કરવાનું. એ સેન્ટરથી તમારે બંને બાજુ જવાનું. ધારો કે મેં એક મોલેક્યુલ લીધો CH3 CH2 CH3, આનો સેન્ટર પાર્ટ આ થયો. હવે હું અહીંયાથી આ સાઈડ આવું, આ સાઈડ આવું, આમ જાઉં કે આમ જાઉં, બધી બાજુ જો સેમ આવતી હોય તો ઇટ કેન હેવ એ સેન્ટર ઓફ સિમેટ્રી. Concept clear? We can consider a center point in a molecule. From this center point we can move any side and we can have same parts or same groups of atoms. Therefore, you can say that this molecule have a center of symmetry. Yes, we can study in this lecture very detailed, but here some example. It cannot have a plane of symmetry, it cannot have a center of symmetry, therefore it shows the optical isomerism. Transform shows the optical isomerism, while cis form does not shows the optical isomerism, because the requirement does not fulfill in this condition, and all requirements are fulfilled in this condition. It not have a symmetry, it is a disymmetric compound. Therefore, you can say that this compound shows the optical isomerism. Yes, now we can think about some another examples. Examples are there: cyclopropane, OH, OH and CH3. If you can think about the chiral carbon, then this molecule have two chiral carbon. First one is this and second one is this. You can check it, because OH, H, here CCH3 and here COH, means that four different valencies. It is also same like that. Now this compound have two chiral center, but it is optically active. Why? Because it can have plane of symmetry. If you can pass the plane from here, CH3 means that C, H, 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 it cut down into two equal parts. Therefore, it can have a plane of symmetry. It can does not shows the optical isomerism. It can does not shows the optical isomerism. Two chiral centers, but does not shows the optical isomerism, because it can have a symmetry, plane of symmetry. Suppose here if we can have a cis 1,3-dimethyl cyclobutane, cis 1,3-dimethyl cyclobutane. Now we can draw it, cyclobutane 1,3 and cis position. If we can have any plane and we can pass from here, it can cut down the molecule into two equal parts. Means that it can have plane of symmetry. It does not shows the optical isomerism. Next one is trans 1,3-dimethyl cyclobutane. Trans 1,3-dimethyl cyclobutane. Means that one is upside, second one is downside. If you can pass the plane, it does not cut the molecule into two equal parts, but because one is upside, second one is downside. Clear? It cannot have a plane of symmetry, but it is not optically active, because it can have a center of symmetry. Because it can have a center of symmetry, and if any symmetry are present, then the compound is not optically active. Clear? What is the center of symmetry? We can write here or we can understand here. Suppose this is the molecule X, X, Y, Y, Z, Z, and we can consider a center point of the molecule in the molecule, not out of molecule. Now from this center we can go through the two different opposite directions, and two different opposite direction we can have same molecule or group of molecules, therefore you can say that center of symmetry is present. That is a definition. So center from go through the two different directions, we can get same groups or atoms is known as center of symmetry. Yes, very simple meaning, equal distance in opposite direction. If we can consider a point and from this point we can have molecules or group of molecules equal distance in opposite direction, it is known as center of symmetry. Here now we can consider the center point of the molecule, we can go through this direction, it is a carbon, here also this carbon. If you can go the downside, CH3 exactly opposite side, CH3 upside, means that this is a center point, therefore the molecule have a center of symmetry and the compound is optically inactive. Clear? Write down this, the center from go through the two different directions, we can get the same groups or atoms is known as center of symmetry, means that equal distance in opposite directions of atoms from the center. Equal distance opposite direction, equal distance opposite direction, equal distance opposite direction, it is the center of symmetry. Now we can think about the some example of center of symmetry. First example is like that, trans-butene, it is like that, C double bond C, CH3H, CH3 and H, trans-butene, it is the center point of the molecule. If you can go through this side and this side, carbon carbon, clear, opposite direction, equal distance, same part, upside and downside also same, CH3 and CH3, CC, CH3, CH3, opposite direction, equal parts, means that center of symmetry may be present. Here CC, HH, center of symmetry may be present, therefore the compound is not optically active. Any doubt? Next, suppose if you can think about cis-butene, it is trans, it is cis, it cannot have a center of symmetry, because if you can go through this direction, it is sufficient, both are carbon. But if you can go through this direction, it is hydrogen. If you can opposite direction, it is CH3. If both are same, therefore you can say that center of symmetry is present. Here both are different parts. Clear? Because we can think about opposite direction. If you can think about opposite direction of this hydrogen, it is this, not in equal direction. Opposite direction, equal parts, center of symmetry. Clear? It cannot have a center of symmetry, but it can have plane of symmetry. You can pass the plane, it can cut down the two equal parts, therefore does not show the optical isomerism. If any symmetry is present, then the molecule does not become optically active. Whatever or how many chiral centers are there in the compound, but it does not become optically active. If you can have a compound like that, CH3H, C, O, C double bond O, O, C double bond O, C, CH3H, and you can consider the center point. We can go through the two different directions, O and O, C and C, double bond O, double bond O. Therefore, you can say that this compound has a center of symmetry. This is not shows the optical isomerism. Clear? Next and very important example is like that, cyclobutane, CH3, COOH, CH3, COOH, upside, upside, downside, downside. If you can think about plane of symmetry, we cannot have any plane which can be exactly divide the molecule into two equal parts, because upside and downside. Half part is in upside, half part in a downside. Now we can think about center of symmetry. It is a center. It is a center. If we can go through the downside, we can have a methyl. If we can go through the upside, we can have a methyl. Means opposite direction, equal distance, same molecule. Center of symmetry is present. If we can go to the upside and downside, COOH, COOH. Therefore, we can say that this molecule have a center of symmetry and does not show the optical isomerism. Means that we can consider a point, center of the molecule, in the center of the molecule, and this point we can go through the opposite direction and we can have same parts or same parts in equal distance. We can say that this molecule have a center of symmetry. Clear? Now if you can think about the example like that, CH3, HBr, HBr and CH3, CH3, HBr, HBr and CH3, here C and C. This is two chiral centers because H, Br, CH3 and this part, 4 different valency. It is also a chiral center, H, Br, CH3 and these parts, 4 different valencies, molecule is 4 different valencies, atom is a chiral atom, clear? Now if you can think about the chiral center, it can have a 2 chiral center, but molecule is optically inactive, but molecule is optically inactive, it does not show the optical isomerism due to the plane of symmetry. If you can pass the plane from this side, it can cut down into 2 equal parts, therefore the compound does not show the optical activity. Now why this type of compound does not show the optical activity, we can show here. Suppose if this part is rotate the plane polarized light through right side, theta direction or theta value, if this part, this upper part rotate the plane polarized light to right side through the theta, then this part also rotate the plane polarized light to the opposite direction. It rotates like that. It is the main direction of plane polarized light. It rotates the left side, same value theta. Therefore the resultant rotation may be 0. Means that if this upper part rotate the plane polarized through that direction, then lower part rotate the plane polarized light like that direction, clear? Means that due to the internal compensation, molecule does not show the optical isomerism, because both parts rotate the plane polarized light through the same theta in the opposite direction. If this part rotate the plane polarized light through this theta, then this part rotate the plane polarized light to this theta in opposite direction, means that the resultant is 0. If it rotate the 10 degree through right side, then it rotate the 10 degree to left side, means that the resultant is 0. First it rotate it, now second it rotate it, means resultant is 0. And this type of compound, in which due to the internal compensation compound becomes optically inactive, is known as Meso compound. But in Meso compound we can think about details in next lecture. Here we can remember it, this type of compound in which due to internal compensation, means both parts rotate the optical plane of polarized light through opposite direction in same theta or in same value. Therefore resultant rotation of plane polarized light is 0, clear? Now we can take the second isomers of this compound. It is a first structure, it is second and third isomers of this compound. Here we can say that CH3 same, HBr same, we can rotate it. Here Br and H, it is a stereoisomer because no difference in connectivity of the atoms. It is the stereoisomers. And third one is also stereoisomer of first, because CH3 here we can rotate BRH and it remains same. It is also a stereoisomer because we cannot change the connectivity. Clear? We can change the position of atoms in the space. Now it is a chiral center. It is also a chiral center because H, Br, CH3 and this part, H, Br, CH3 and this part, it can have 2 chiral center. Now we can check the symmetry. If you can think about the plane of symmetry, we cannot have any plane if we can pass through this. Therefore it is a don't equal part because here Br and here H and Br, CH3, तो कोई मतलब नहीं. Next, if you can pass the plane from this direction, it is H and Br, it is Br and H. Therefore no plane of symmetry. If you can consider a center, if you can goes through the opposite directions, therefore center of symmetry is also does not present. Clear? Now we can say that this molecule is optically active. Center of symmetry does not, because if you can go through this direction, here we can have a methyl group. Clear? And same. Therefore no center of symmetry, 2 chiral center, no plane of symmetry, no center of symmetry. This compound is optically active. And remember that if any compound is optically active, it can have another isomer which is its enantiomer. We can draw the mirror image of this compound. It is like that. Mirror image we can draw. આ સાઇડના મોલેક્યુલ આ સાઇડ દોરવાના, આ સાઇડના મોલેક્યુલ આ સાઇડ દોરવાના, CH3. It can have two chiral center. It is also optically active because no plane of symmetry, no center of symmetry, and this compound is known as pair of enantiomer. The compound which are mirror images of each other and which are non-superimposed on each other is known as enantiomer. Therefore, we can say that here first and third are enantiomers. Here first and third are enantiomers of each other because it is non-superimposable mirror images. How we can superimpose? First we can rotate the molecule through 180 degree and then we can superimpose it. It is not superimposed, therefore we can say that it is optically therefore it is optically active and the compound is a pair of enantiomers. Suppose if you can think about this, 2 and 3 are stereoisomers. In stereoisomer, it is non-superimposable mirror images. Therefore, these are the enantiomers. These two structures are the enantiomers. If 1 and 2, if you can think about 1 and 2, it is stereoisomer, but not mirror image. It is not a mirror image of this compound. સુપરઇમ્પોઝની તો વાત જ નથી, મિરર ઇમેજ જ નથી. જો મિરર ઇમેજ ન હોય તો એને મિત્રો કહેવાય ડાયાસ્ટીરિયોમર. Therefore these two are the diastereomers of each other. These two are the enantiomer of each other because mirror image is non superimposed. These two are not a mirror image, only stereoisomer. Therefore it is a diastereomers. Therefore it is diastereomers. Now we can think about 1 and 3. In 1 and 3 it is stereoisomer because connectivity is different. No connectivity is different, only space arrangement is different. Non-mirror images. Therefore, you can say that 1 and 3 are also a diastereomer. This is the pair of diastereomer. This is the pair of diastereomer, and this is the pair of enantiomer. Clear? Now, we can think that about diastereomer. Stereoisomers which cannot be a mirror images of each other is known as diastereomer. The compound which are not a mirror images of each other is known as diastereomers. Now we can think about this compound COOH, HH, C and C. These both are chiral center. But this isomer is optically inactive due to the Meso compound. Because if we can pass the plane, it can cut the molecule into two different sides. If this molecule rotates the right side, this molecule rotates the left side, plane polarized light. Therefore, resultant rotation is 0 and molecule does not become optically active. Clear? And this type of compound is known as Meso compound. Now we can change the space arrangement. COOH, CC, HOH, OHH. આપણે એકને ચેન્જ કર્યું, સ્ટીરિયોઆઇસોમર બન્યો. Clear? And if you can think about that, it is two chiral center, no plane of symmetry, no center of symmetry. Therefore, you can say that molecule is optically active. If a molecule is optically active, then we can draw the mirror images of each other because it can have an enantiomer. That is COOH, OH, OH, HOH. It is a mirror images of this compound, and these mirror images are the non-superimposed on each other. Therefore, you can say that it is a pair of enantiomer and both are optically active. In this, second and third is enantiomer because non-superimposable mirror images. 2 and 1 is diastereomer because not a mirror image. 1 and 3 is also a diastereomer because not a mirror image. If a mirror image and then superimpose on each other, therefore you can say that it is enantiomer. If not a mirror image, therefore you can say that diastereomer. Always remember that, friends. If you can think about all geometrical isomers, it is a, if you can think about all geometrical isomers, it is a stereoisomer. It is a stereoisomer, and from this stereoisomer, if you can have any compound which is a non-mirror images, It is diastereomer. Very easy. How we can find the diastereomer? If we can have any geometrical isomer which is stereoisomer, it is confirmed. From these, non-mirror images are the diastereomers. So we can complete here. Some symmetry operations like plane of symmetry and center of symmetry, and we can take the example of it and how the compound become optically inactive due to the plane of symmetry because of the internal compensation. Both part rotate the plane polarized light toward the opposite direction. If this part rotate the right side, then this part rotate the left side, then the resultant rotation is 0. So I hope you can understand the enantiomers, diastereomers and meso compound, but we can discuss very detail in next lectures about meso compounds, enantiomers and diastereomers. In next lecture we can take some examples and questions of this lecture. Clear? So you can understand very easily diastereomer, enantiomer and meso compound. Yes, you can practice the plane of symmetry and center of symmetry in different types of examples. In next lecture we can discuss about some questions and examples.